So, in today's class we shall discuss about the Diffie-Hellman problem and security of ElGamal systems. So, the objectives of today's discussion will be the Diffie-Hellman problem, and we shall essentially continue with the discrete logarithm problem which we saw in the last class, and we shall discuss about the bit security of these discrete logs and conclude with some comments on the semantic security of the ElGamal systems. So, just as a reminder that as we have studied in the last class, that in the discrete logarithm problem we essentially have a finite group of elements, and for an element alpha which belongs to G and which has an order of n, we can actually define a group by raising alpha to its various powers. Okay, so where like computing alpha power I, where I ranges from 0 to n minus 1, we can obtain all the elements of the group. Now, as we remember that the problem of discrete logarithm was to find out the unique integer I when we are given alpha and beta, where alpha and beta satisfies the relation that alpha power of I is equal to beta. So, the question is, given alpha and beta, we have to find the value of I. So, I is often referred to as log beta base alpha, which is often referred to as the discrete logs. So, we discussed in the last class and saw some cryptanalytic methods of how to obtain this value in under certain special cases. So, the discrete logarithm problem was essentially the inverse of the exponentiation operation, and it is believed to be hard. That is, it is believed that for proper choices of the parameters, computation of the discrete logarithm problem is a difficult mathematical problem. Now, it has got various applications. For example, we have studied the application of discrete logarithm problems to the ElGamal cryptosystems, where essentially we have got two components in the ciphertext. Suppose we want to encrypt a plain text, say x, or then what we do is that we essentially choose the constants of the group. For example, we choose the prime value, we choose alpha and beta, which are essentially public values, but A which is a secret, right. So, therefore, A is a secret and A is the logarithm of beta with respect to alpha, that is the discrete logarithm. So, the difficulty is that if we are given alpha, beta and also the choice and also the value of p, it is assumed that computation of A is a difficult problem. Now, based upon this assumption, in this encryption scheme, what we have seen is that if we want to encrypt, for example, x, where x is a plain text value which belongs to ZP star, then what we do is that we essentially choose a random number r which belongs to ZP minus 1. Okay. And then what we do is that we choose this r which is a random number and compute using x and r two parts of the ciphertext. One part is y1, the other part is y2. Now, essentially in y2 what we do is that we actually blind or mask the value of x by multiplying it with beta raised to the power of r, and in the other part of the ciphertext we actually compute alpha power of r modulo p, right. So, therefore, these two things are actually transferred to the receiver who has the knowledge of the value of A. Now, if it has got the knowledge of A, then what it does is that it raises the part of, that is y1, the first part, to A, which is a secret, and computes the value of alpha power of AR, and alpha power of AR is nothing but beta power of R. So, that means the receiver can now compute the inverse of beta power of R and multiply it with y2, okay, and retrieve back the value of x. Now, it is believed that the person or the attacker who does not have the knowledge of A, right, cannot compute this inverse, because that is the challenge. So, therefore, if from y1 and y2 if the attacker is able to obtain the value of A, that means it is able to solve the discrete logarithm problem, then essentially this cipher can be compromised. Okay. And based upon the assumption that the discrete logarithm problem is hard, we actually have got this crypto system which is popularly known as the ElGamal cryptosystem. Now, in today's class we shall discuss about two things essentially. We shall discuss about that, okay, the discrete logarithm problem is hard, but is it also difficult to obtain the bits of a discrete log? That is, for example, is it really difficult to obtain the 0th bit? Is it really difficult to obtain the first bit? Is it really difficult to obtain the ith bit? That is one part of the discussion. The other part will be to reflect upon the crypto system of ElGamal with respect to semantic security. So, what is semantic security? So, we have seen that in context to some of the ciphers like RSA is that if we are given two plain texts like x1 and x2 and we are given a cipher text. Okay. So, that means we know that either x1 or x2 has been encrypted, but we do not know which one has been encrypted. Now, the problem is that from y, that is a cipher text, if we are able to kind of guess that whether x1 has been encrypted or x2 has been encrypted, then we say that it is a violation of the semantic security. So, therefore, a good crypto system, a crypto system which is semantically secured, should also protect against such kind of information leakage. Okay. So, we shall study that whether the ElGamal crypto system also belongs to such kind of semantically secured cipher. Okay. So, we shall continue with this problem, and also another we will discuss about another application of this discrete log problems. It is to something which is called as the Diffie-Hellman problem. Okay. Now, Diffie-Hellman problem is essentially a very interesting way of doing key exchanges often. Okay. So, first of all, let us study what is the problem. So, the problem generally comes in two flavors. One is the computational problem and the other is a decisional problem. So, therefore, it is important that when you are discussing about the computational problem, that essentially to understand about what is the problem. Okay. So, the problem is, in this case we are being provided with a group which is G, and the product here is dot, defined as dot. Okay. And we are provided with an element alpha which belongs to G and which has got an order of n. Okay. And we are provided with two elements like beta and gamma which belongs to this group. Okay. So, beta and gamma belonging to this group, we know that beta is nothing but alpha raised to some value and gamma is also alpha raised to some value, right. Now, our question is that therefore to find another value which is delta, which belongs to this group also, such that the logarithm of delta to the base a is equal to or congruent to the logarithm of beta base alpha multiplied with the logarithm of gamma base alpha. Okay, where we are all doing modulo n computations. So, the question is, I mean, it can equivalently be stated like this, that is, we are being provided with suppose two values like alpha power of b and alpha power of c. Okay. So, therefore, assume that beta and gamma, as I have told you, that can also be written as alpha power of some value like b, and similarly gamma can also be written as alpha power of c, right. It is alpha raised to some value. Okay. Now, the question is, given these two values like alpha power of b and alpha power of c, can we compute alpha power of bc? That is the problem. Okay. So, the computational Diffie-Hellman problem says us that given this group description and given these two elements like beta and gamma, can we compute this value of log, so can we find out the value of delta such that this equation is satisfied. Okay. The other one is that it can equivalently be stated like, if we are provided with alpha power of b and alpha power of c, can we compute the value of alpha power of bc. So, that is the computational Diffie-Hellman problem, or as is often referred to as the CDH problem. Okay. So, in this case we know that so if I write it in a very small way, that is summarize what is the computational Diffie-Hellman problem, it means that we are provided with two values like alpha power of b and we are provided with another value like alpha power of c. Can we compute the value of alpha power of bc? Okay. Or okay. So, such that here beta essentially means alpha power of b and gamma means alpha power of c. Okay. So, therefore, here you are basically you are supposed to compute the value of delta such that this equation is satisfied. Okay. So, that means if you are provided with two values like alpha power of b and alpha power of c, can you compute the value of alpha power of bc? that is the computational Diffie-Hellman problem. Now, the decisional variant of this problem, or as is called the decisional Diffie-Hellman problem or DDH, is slightly different. The problem statement here is that we are provided with alpha power of b and alpha power of c, and we are also provided with another alpha power of d. Okay. Now, the question is that does d satisfy the value of bc? Okay. So, that is the problem, that is, does d satisfy the value of b multiplied by c. Okay. So, therefore, this is the question, that is, does d satisfy this particular relation. So, we can understand, like, I mean, an obvious question would be like, so we have essentially seen three problems, right. We have seen the discrete log problem, we have seen the computational Diffie-Hellman problem, and we have seen also the decisional Diffie-Hellman problem. So, one obvious question is their relative hardness. Are all of them equivalent, or is that one problem is more difficult than the other problem, right. So, therefore, you can just see this statement. It says that the Diffie-Hellman problem, so DDH, okay, so you can actually do polynomial, I mean, in polynomial time, or rather you can do reductions between these problems. Okay. So, first of all, let us see that, for example, if you have a solution to the discrete log problem, then first of all try to reflect that you can actually solve the computational Diffie-Hellman problem. Okay. Why? Because you see that if you can solve the discrete log problem, then you can easily obtain, I mean, for example, assume that if you can solve the computational Diffie-Hellman problem, that is, if the computational Diffie-Hellman problem is not hard. Okay. So, then you can actually solve, or rather if you assume that the discrete log problem is not hard, I mean you can solve the discrete log problem, then you can actually solve the computational Diffie-Hellman problem. Why? Now, because if we are provided, so what is the computational Diffie-Hellman problem challenge? That we have been provided with alpha power of b and alpha power of c, right. So, if you can solve the, if you have a mechanism to solve the discrete log problem, then from alpha power of b you can compute the value of b. Similarly, from alpha power of c you can compute the value of c. So, you can compute the value of b into c, and therefore, you can also obtain the value of alpha power of bc, right. So, this is trivial. You see that trivially, if you can solve the discrete log problem, then you can solve the computational Diffie-Hellman problem. So, that means in terms of hardness, we will say that the computational Diffie-Hellman problem, if it is hard, okay, then that is, if the assumption that the computational Diffie-Hellman problem is hard, then it also implies that the discrete log problem is hard. Okay. So, therefore, we will say that is one kind of one part of the understanding of the relative hardness. Okay. Now, you see the other part, that is, if the computational Diffie-Hellman problem is not hard, that means if you have a mechanism to solve the computational Diffie-Hellman problem, then you also have a mechanism to solve the decisional Diffie-Hellman problem. Now, this is also very trivial, because you see that if you can, so this is your decisional Diffie-Hellman problem, right. That is, you have been provided with alpha power of b, alpha power of c, and alpha power of d, and you have to check whether alpha power of d is equal to essentially, I mean, if d is congruent to b into c, right. So, you see that if you can solve the computational Diffie-Hellman problem, then given alpha power of b and alpha power of c, you can compute the value of alpha power of bc, right. So, now what you can do is that you can just check that whether alpha power of bc is indeed equal to alpha power of d, right. If alpha power of bc is equal to alpha power of d, then you can conclude that d is indeed congruent to b into c, and hence solve the decisional Diffie-Hellman problem. So, therefore, you can also similarly state that if the assumption that the decisional Diffie-Hellman problem is the difficult problem, is a hard problem, then it implies that your computational Diffie-Hellman problem is also a difficult problem, right. So, therefore, we can actually conclude this line that the DDH hardness, okay, is at least as strong as the computational Diffie-Hellman hardness assumption, which is at least as strong as the discrete logarithm problem hardness assumption, right. So, do you understand this? That is, so therefore, what I am essentially doing is that I am just writing this in kind of combining these two things, and we are writing that the DDH assumption implies that implies the CDH assumption, which implies the discrete log problem assumption. Okay. So, that means that this problem, this assumption, okay, that is the DDH hardness, is at least as strong an assumption as that of the computational Diffie-Hellman problem assumption, which is at least as strong an assumption as the discrete log problem assumption, right. Okay. So, now let us reflect another kind of interesting such equivalence or reduction, that the security of the ElGamal cryptosystems is equivalent to solving the computational Diffie-Hellman problem. Okay. So, let us see. So, therefore, if I say it is equivalent, then I have to show that if I can solve the ElGamal cryptosystem, then I can obtain a value of the I can solve the computational Diffie-Hellman problem also. Similarly, the other way, that if I can solve the computational Diffie-Hellman problem, I should have a mechanism to solve the ElGamal cryptosystem also. So, here let us assume that there is an oracle called CDH which solves the computational Diffie-Hellman problem. Okay. So, what does it mean? That means if it is given, so that means that I have an oracle, call it oracle CDH, okay, which takes a value of alpha, beta and y1. Okay. So, what is y1? Y1 was equal to alpha power of r according to our ElGamal cryptosystem, right. So, if I take the value of this, then if I have been provided with this, and what was beta equal to? Beta was equal to alpha power of a, right, that is the secret value. So, now if I am able to solve the computational Diffie-Hellman problem, then this means that from these two values I should be able to compute the value of alpha power of ar. I should be able to compute the value of alpha power of ar. Okay. So, call this as delta. That means you get a value of alpha power of ar using an oracle which is able to solve the computational Diffie-Hellman problem. So, now one can actually decrypt and obtain the value of x using this. How? Now, because you know that if you are able to obtain the value of alpha power of ar, then alpha power of ar is nothing but beta power of r, right, and you know that y2 was equal to x multiplied by beta power of r, right, that is nothing but x multiplied by delta, right. So, therefore, in order to find the value of x, I just need to take y2 and multiply it with the inverse of delta. Okay. So, that means whatever the oracle to solve CDH problem gives me, I take or compute the multiplicative inverse and multiply it with y2, I obtain the value of x, right. Now, that explains one direction of the problem. We have another direction to prove, right. So, in that case, what we will do? We will assume that there is an oracle which solves the ElGamal cryptosystem, right. So, assume that there is an oracle which solves the ElGamal cryptosystem, okay, and it takes in again two values like alpha, beta and of course, the ciphertext y1 and y2, and gives back what? It gives back the value of x, because that is the objective of this oracle, right. It basically deciphers the value of the plain text from y1 and y2. So, therefore, it returns back to me x. Okay. So, now we know that this relation is true, right. We know that x is equal to y2 into delta inverse. So, therefore, you see that trivially that you can actually obtain the value of delta which is equal to y2 into x inverse, right. And what is delta? We have discussed, right, that if you can calculate the value of delta, then you are essentially solving the computational Diffie-Hellman problem. Okay. So, that means that if you can solve the ElGamal cryptosystem, then you can also solve the computational Diffie-Hellman problem. So, therefore, you know that CDH assumption is equal to that ElGamal assumption, and similarly you see that the ElGamal assumption is also implying. So, therefore, the CDH assumption is implying the ElGamal assumption. Similarly, the ElGamal assumption is implying the CDH assumption. So, therefore, we will say that the ElGamal assumption is equivalent to the CDH assumption, right. Is clear? So, now we shall go into into an application of the Diffie-Hellman problem. It is a very interesting application of how to solve the key agreement scheme. So, we have discussed like in context to symmetric ciphers that you, for example, if there is a network with say n nodes, then you need to kind of exchange keys between all of them, right. That is a huge amount of key exchange. So, which means that it is a very important problem to solve how to exchange the keys between two parties. So, we will see that the discrete, I mean the Diffie-Hellman problem essentially was propounded, I mean one of the strongest application of probably of Diffie-Hellman problems is to solve the key agreement scheme, okay, that is to give a solution for key agreement. So, we see that this is the setting, like you have a public value of G and P, which are two public quantities, and there is a secret, that is Alice has got a secret component called A and Bob has a secret component called B. Okay. So, therefore, what they do is this, that is Alice computes G power of A modulo P, that is it takes the public quantity G, raises it to A and computes modulo P. Okay. The other part is that Bob also computes the value of G power of B modulo P and obtains the G power of B modulo P and sends it to Alice. Okay. So, now the objective of both Alice and Bob will be to reach a common consensus, that is to reach an agreed point. Okay. So, what Alice does is this, that is Alice takes G power of B modulo P, because that is the part which it receives from Bob, and raises G power of B modulo P to its secret value A. Okay. So, therefore, if I raise G power of B, raise it to A, then I obtain G power of B A, but that is equal to G power of A B mod P, right. So, what Bob does is the other way, that is Bob has got G power of A modulo P from Alice, and what it does is that it raises it to the power of B. Okay. And therefore, you see that both Alice and Bob essentially have computed the value of G power of A B modulo P, right. Now, this is essentially used as a symmetric key for further encryption. So, therefore, if I want to use AES, DES and other symmetric ciphers, then I can use this exchanged key as my computed symmetric key, right. So, now you see that you can reflect upon the difficulty of the problem, that is why can't a person who does not have a knowledge of the secret values A and B is able to compute the value of G power of A B mod P. Okay. So, you see that is precisely the Diffie-Hellman assumption, that is if I am provided with G power of A mod P and with G power of B modulo P, then I should not be able to compute the value of G power of A B modulo P, right. Or even the Diffie-Hellman, the decisional Diffie-Hellman problem says us that even if I am provided with a G power of D modulo P, I should not be able to say that okay, this G power of D modulo P has got this nice property of being equal to G power of A B modulo P. I should not be able to even decide that. That is a decisional Diffie-Hellman problem, right. So, you have a computational as a flavor and you also have a decisional flavor of the same problem, right. But you see that you can actually reflect that there is a very small, I mean, so these are a kind of something which is called as passive attacks. Okay. But what if you also can do an active attack? So, you see that the Diffie-Hellman key exchange actually does not give you any guard against that. For example, you assume that there is a party called Trudy who comes in between, okay, and what it does is this, that is it takes G power of A modulo P and just changes it to something like G power of T modulo P. Okay. So, therefore, this G power of A modulo P is now not, I mean I am not solving the decisional Diffie-Hellman problem, but I am just modifying it to something like G power of T modulo P. Now, this kind of modifications is commonly referred in the cryptographic literature as man in the middle attacks. Okay. So, this is an active attack, no doubt. Okay. So, similarly, now you see that Bob computes G power of B modulo P, but Trudy just modifies it to something like G power of T modulo P, right. Now, you see that both of these parties, what it will do is that Alice will raise this G power of T modulo P to its own secret. Similarly, Trudy, we can actually raise G power of A modulo P to its own secret T, right, and obtain G power of AT modulo P, right. Now, what about Trudy and Bob? Both of them actually computes the value of G power of BT modulo P. So, now you see that both Alice and Trudy can actually continue their communications using the secret key g power of at modulo p. Okay. What about Trudy and Bob? They can actually compute using, continue communications using g power of bt modulo p. But you note one thing, that Alice does not know that Trudy exists, Bob also does not know that Trudy exists. So which means that it is a problem, right, because you see that Alice and Bob are supposed to communicate between each other, while in the network actually Alice is computing with an untrusted party or an attacker without knowing that it is actually intruding its information. Okay. That is knowing that the actual information or the actual intended receiver of the information is not receiving the information. Okay. So this is a clear breach of the security, right. So therefore I see that this is a very something that we need to kind of guard against. Okay. So therefore the man in the middle attack on the Diffie-Hellman key agreement scheme shows that although our primitives are strong, your protocol can be weak, right. So we till now we have been actually trying to kind of design strong primitives, right, but we see here that although your primitives are strong, but your application can be weak. Okay. So therefore the next question can come like how to design strong protocols from strong primitives. Okay. So that is a kind of a very kind of a pertinent research problem. Okay. So here so therefore you have got the entire domain of cryptographic protocols and how to design protocols. Okay. So there are some possible preventing techniques, like for example I will encrypt the Diffie-Hellman exchange with symmetric key, I will encrypt the Diffie-Hellman exchange with public key. Okay, I will sign the Diffie-Hellman problems with private keys. So there can be some afterthoughts like how to prevent the man in the middle attack, but the point is that remember that the Diffie-Hellman key exchange as stated, okay, as per the basic definition, is not secured against man in the middle attack. You have to do something extra. Okay. But anyway, we will not continue with this right now, but we will rather continue with the bit discrete log problem and reflect upon the mathematical problem of the bit security of discrete logs. Okay. So what we will first discuss is this problem, that is the discrete log ith bit problem. Okay. So what is the problem first of all? The problem is that we have been given an instance like again what we have seen previously, prime number p, alpha, beta and a value of I. Okay. Here your alpha belongs to zp star, beta and is a primitive element, beta also belongs to zp star and I is an integer which lies between 1 and logarithm of p minus 1 base 2. The problem that we are considering right now, or what we are referring as the discrete log ith bit problem, is this, that is to compute Li beta, that is given beta and where beta is equal to alpha power of a. The problem is that to essentially compute the value of the ith least significant bit in the binary representation of log beta base alpha. Okay. So your logarithm of beta base alpha is denoted as a, right. Now you know that a can be represented using a binary values. So I can start like with x0, x1 and so on, right. So my problem when I am considering the Li beta, okay, is to compute the value of xi or rather xi minus 1. Okay. So my problem is to essentially compute the value of the ith bit. Okay. So when I am referring to L1 beta, I am compute the value of x0. When I am referring to Li beta, I am computing the value of xi minus 1. Okay. So that is a problem. So you can say that okay, this x0, that depends upon your numbering. You can also number it from x1 to x2 and so on, just to avoid a confusion. So you can say that L1 beta actually refers to x1 in that case, and xi minus 1 refers to xi. Okay. That is just to avoid the confusion of these the indices. Okay. So anyway, the problem is to compute the ith least significant bit. Okay. So we can actually see that for solving for I equal to 1 is very easy, that is to compute computing the least significant bit of a, that where a is equal to log beta base alpha, is actually very easy. So why? So for this we will actually use our previous idea of something which is called as quadratic residues. So we have studied quadratic residues in context to RSA, right, we discussed about RSA. So what was quadratic residue? Quadratic is an element was said to be quadratic residue if you can actually represent it by the square of another element, right, in that group. So, then we refer that to as a quadratic residue. So, therefore, if I say that beta equal to alpha power of a, then if this is a quadratic residue, then this is actually if and only if condition is that a has to be even. Okay. So, therefore, you need to compute. So, therefore, beta will be a quadratic residue if and only if a is even. Okay. And from Euler's criteria, which we have studied also previously, we know that if beta beta is a quadratic residue of modulo p if and only if, the way of checking that is by raising beta to the power of p minus 1 by 2 and checking that whether it is congruent to 1 modulo p, right. So, what can be the possible values of beta to the power of p minus 1 by 2? It can be either plus 1 or it can be minus 1, because you see that from Fermat's little principle beta power of p minus 1 is equal to 1, right. So, it can be either plus 1 or minus 1. So, you see that if it is equal to plus 1 modulo p, then beta is actually a quadratic residue. Similarly, beta is a quadratic residue implies that this is an if and only if condition, necessary and sufficient, right. So, you see that therefore, if I club these 2 points, what does it mean? It means that I have to obtain L1 beta, right. So, we are computing the least significant bit. Now, if this is an even value, that is if a is even, then what is the value of L1 beta? It is equal to 0, because only then the exponent is even, right. So, you see that if it is even, right, what it says is that then there is an if and only if condition, it is equivalent to saying that beta is a quadratic residue, and if beta is a quadratic residue, then it is equivalent to compute this value. So, therefore, what will you do is that you will take beta and raise it to the power of p minus 1 by 2 and check whether it is equal to 1 modulo p, congruent to 1 modulo p. If that is so, then you conclude that a is even and therefore, L1 beta is 0, right. Otherwise, it is odd and hence 1, right. You see this. So, this is an efficient way of understanding the 0th bit or the first bit, the least significant bit. So, that means what? That means that although the discrete log problem is believed to be a difficult problem, but actually the 0th bit is easy to compute, or the least significant bit is easy to compute. So, you see that these 2 problems are difficult, are different, like right, that computing the value of the discrete log problem is not exactly the same as compute an ith bit of the discrete log, right. So, you see that it is very easy to compute the least significant bit. Now, the question is it also difficult to compute any bit, the first bit, second bit and so on, because you see that there is a danger, right, because if I am able to retrieve all the bits, then essentially I can solve the discrete log problem, right. So, therefore, the question is whether the next bit is also difficult or the next to next bit is also difficult. Okay. So, we will first of all consider a special case where p is congruent to 3 modulo 4. Okay. So, in this case, why we are talking about p being congruent to 3 modulo 4, I will talk about that later, but first of all let us discuss about this case, like p is congruent to 3 modulo 4. Okay. So, you note that if p is congruent to 3 modulo 4, then so for example, if you can refer like p, right, you can always write like p minus 1 for example as p minus 1 is an even value, right. So, therefore, you can always write it as some 2 power of s, right, multiplied with some t value, where t is not a multiple of 2, that is t is an odd value, right. So, therefore, if I take the base the minimum case where s, so s is greater than equal to 1. So, I take the s case s equal to 1. Okay. If s is equal to 1, then it means that p minus 1 is equal to 2 into t, right. So, you see that this p equal to, so that means that p is congruent to 3 modulo 4, because if you take p and if you subtract like 1, so it becomes 2, right. So, then it becomes 2 modulo 4. Okay. So, therefore, this is the base, the first case when we consider this case, that p minus 1 equal to 2 power of s t, okay, then I am considering the case that s is equal to 1, and hence I am considering the case when p is congruent to 3 modulo 4. Okay. So, therefore, if p is congruent to 3 modulo 4, then we will see a very interesting case, that is if we have an oracle to solve the value of L2 beta, that is compute the value of L2, we have seen that L1 beta is easy, right. So, if we actually can you compute L2 beta, then we can use that to obtain the value of the discrete log. That is, we can solve the discrete log problem in the prime field. Okay. So, now in order to understand the algorithm, we have to see some facts, we have to prove some facts. Okay. So, first of all, let us start with this, that is, if the square root of beta exists, okay, that is, beta is a value which is given to me, and assume that the square root of beta exists. So, if the square root of beta exists, then we know that beta is a quadratic residue, right. That means beta power of p minus 1 by 2 is congruent to 1 modulo p from the Euler's criteria, right. So, what we do is that we multiply now both sides by beta. If you multiply both sides by beta, then you have got on the left side beta p plus 1 by 2, because you multiply by beta, so it plus 1 gets added, and on the right hand side you have got beta modulo p, right. Now, what is beta modulo p? We know that beta modulo p is nothing but alpha power of a modulo p, right. And you know that if and only if that, I mean, beta is a quadratic residue if and only if a is even, right. So, which means a by 2 exists and is an integer. So, therefore, we can say that plus minus beta p plus 1 by 4 is congruent to alpha power of a by 2 modulo p, right. That means, if the square root of beta exists, then the square root can be obtained by computing plus minus beta to the power of p plus 1 by 4. So, now note that we are talking about the case when p is equal congruent to 3 modulo 4, right. So, therefore, you see that p plus 1 by 4 is actually an integer, right, and that is why we actually if I want to compute the square root of beta, then I can actually compute beta to the power of p plus 1 by 4 plus or minus. Is it okay? So, you see that if p was not equal to 3 modulo 4, then I would not have been sure that this is an integer, and hence I could not have said that this is the square root. Okay. But here, since this value is given to us, we can say that, okay, if I want to compute the square root, I can compute beta to the power of p plus 1 by 4 plus or minus are the square roots, right. And you also note one thing, that is, if I compute the value of alpha, some value like take any value like gamma square, and p minus gamma square is same when you are doing a modulo p and p is a prime, right. So, that means you have got essentially exactly p minus 1 by 2 quadratic residues, we discussed about this, right, and these two values are different, like this gamma and this p minus gamma are different. Okay. So, therefore, if you have got this plus, so therefore, if I want to compute the square root, then I know that it is either plus beta to the power of p plus 1 by 4 or it is minus beta to the power of p plus 1 by 4, right. And we also know that if one of them is gamma, then the other one will be p minus gamma, because there are only 2 square roots, right. If the square root exists, then there are 2 square roots. Okay. So, therefore, the question is that I know that, okay, alpha power of a by 2 is congruent to plus minus beta to the power of p plus 1 by 4 modulo p, but the question is which one is correct. Okay. That is, which is the actual square root. So, for that we will use this fact, that is, you see that I know that L2 beta is the second bit of beta, right. Now, when you are computing alpha power of a by 2, right, then essentially it is the first bit. So, can you see that L1 alpha to the power of a by 2 is actually equal to L2 to the power of, I mean, L2 beta, right, because you know that when you are taking the square root, right, then essentially, so first of all you know that the square root exists. That means, if you think in terms of like x, like think in a bit like x0, x1 and so on, then your x0 is 0 because the square root exists, right. So, for example, if I write this a would be what? A would be like something like x0 plus 2x1 like so on, right. So, therefore, if I I know that since the square root of alpha power of a exists, that means this is equivalent to saying that if the square root of this exists, equivalent to saying that a is even. So, that means is equivalent to saying that x 0 is 0. Okay. So, that means your a is actually this plus 2 x 1. That means you can compute the value of a by 2 and that will be equal to this plus x 1, right. So, therefore, what is the value of L 1 of alpha power of a by 2? That will be the value of this right, that is the first bit, that is equal to x 1, and that is exactly equal to that of L 2 of beta, because in that case this one was the second bit, right. So, therefore, L 1 alpha power of L 1 alpha power of a by 2 is equal to L 2 beta, right. So, therefore, what you can do is that if you can check that okay, if I just check this, so I know that beta to the power of p plus 1 by 4 is a probable square root, I compute L 1 of that and check whether it is equal to L 2 beta, right, if I can compute L 2 beta, of course, right. So, if yes, then alpha power of a by 2 we will say is congruent to gamma, which is equal to beta to the power of p plus 1 by 4, else alpha power of a by 2 will be congruent to p minus gamma, because that is the other probable square root, right. So, that means either this is the square root or this is the square root. Okay. Agreed on this? So, now we will actually see the steps to obtain the entire discrete log. Now, you know that a, which is equal to log beta base alpha, is nothing but this is equal to xi, and you multiply it with 2 power of I, right, to obtain the entire decimal value of a. So, therefore, you see that alpha power of, so if you obtain the value of beta, then beta is equal to alpha power of like something like x 0 plus 2 x 1 plus so on, right. So, therefore, L 1 of beta, we can actually use L 1 of beta, because we saw that it was an easy problem to obtain the value of x 0. So, one can easily obtain the value of x 0 by the previous technique that we have seen, right. So, now the question is how to now the question is that as we have discussed, that we will assume that somebody can compute the second bit, can compute the value of L 1 beta, or rather can compute the value of L 2 beta, and from there try to obtain the value of a. Okay. So, therefore, what we will do is this, that is we will take we will adopt a method like this, we will take beta and compute the value of beta divided by alpha power of x 0. So, if I take beta and divide beta by alpha power of x 0, then that is equal to what, alpha to the power of 1 plus 2 x 1 modulo p. So, basically what we have done is just taken out the part for alpha power of x 0, this is the part which remains, right. So, now the square root of beta exists for sure. Why? Because you know that this is an even value, the exponent is even, right. So, what we do is that we compute the value of gamma, which is equal to beta to the power of p plus 1 by 4. So, note that beta has been updated by this value, do you see that. So, we compute the value of beta to the power of p plus 1 by 4. Now, you obtain, in order to obtain the actual square root, because you know that there is a dilemma, because this is plus beta power of p plus 1 by 4 or p minus that. Okay. So, what we do is that we compute x 1 from the oracle to compute L 2 beta. So, assume that there is an oracle which actually computes the value of L 2 beta. Okay. So, that is the way how we do the proofs, right. So, we assume that there is an oracle which computes the value of L 2 beta and gives the value of x 1. So, now we can check that whether x 1 is indeed equal to L 1 gamma, right. We have actually obtained the value of gamma, and I know that computing L 1 gamma is easy. So, I can actually compute the value of L 1 gamma and check whether it is equal to the value of what oracle L 2 beta returns, right. If this is so, then the square root of beta is indeed beta to the power of p plus 1 by 4, else it is equal to p minus that, right. So, basically at each stage you are sure about what is the square root, right. So, therefore, you can continue this method like this. Okay. So, you see that we continue this process of the oracle beta to obtain the bits x 2, x 3 and so on to obtain the value of the discrete log in this fashion. Okay. So, summarizing, This is the algorithm, the final algorithm. That is, what you do is this, that is, you take. So therefore, the objective of this is using L2 oracle to solve the discrete log problem. Okay. So I have been given with p, alpha and beta. My objective is to compute the value of a. So what I first do is that I obtain the value of x0 by computing the value of L1 beta, right. So then I compute the value of beta is equal to beta by alpha power of x0 modulo p, because I know already the value of x0, I can compute alpha power of x0, and then I start a running index I equal to 1, and until and unless while beta is not equal to 1, what we do is this, we calculate the value of xi, which is equal to the what oracle L2 beta returns, okay, and compute the value of beta to the power of p plus 1 by 4. Okay. And now we check that whether if Li gamma is equal to xi, if Li gamma is equal to xi, we will say that beta is equal to gamma, because then beta is the square root, otherwise p minus gamma is the square root. Okay. Then we again compute the value of beta by dividing beta by alpha power of xi. Okay. So that means you see that at each stage we are actually taking out we are computing the square root, right. So that means that if you have been given, like say for example alpha power of so on. So for example, first of all you have got like plus 2x1 plus x0, you have divided this by alpha power of x0, that was the first step, right. And from there you compute the value of alpha so on plus 2x1, and you know that the square root existed because this one was an even quantity, right. And then what did you do? You basically took out, I mean you confirm the square root of this, right. And what will be the square root of this? The square root of this essentially will be like, you essentially are computing you are raising this value to the power of half, right. And once you compute the square root of this, again you have got like something like alpha this thing plus x1, right. So you have got 2, here you have got 2x2, you see that. So now if I divide again this by alpha power of x1, I again have this, right, alpha so on plus 2 of x1, right. That means sorry 2 of x2, right. So that means I know that again that the square root of this exists, because this is again an even number, right. So that means again I can confirm the value of square root, and I know that if I confirm the value of square root, then I am again raising this to the power of half, right. So again it becomes something plus x2, so again I divide that alpha power of x2, right. So what you are basically doing is that using this oracle which solves the L2 beta, okay, you are actually confirming the value of the square root, okay, and from there you are actually dividing that contribution and computing the discrete logs gradually, one after the other. You are obtaining the bits, and if you are able to obtain all the bits, then you essentially solve the discrete log problem. So that is the basic algorithm to solve the discrete log problem. Now some final comments of this would be like, the proof holds for any p where p is equal to for p minus 1 is 2 power of st. So we told you that this actually holds for any p minus 1 where p minus 1 is equal to 2 power of s into t, okay. So it does not necessarily hold only for p is congruent to 3 modulo 4, but we can actually have a similar result when p minus 1 is congruent to, or rather is equal to 2 power of st, where s is an integer, okay. So in that case we will see that I mean using the previous thing we can reflect that obtaining s LSBs will be easy, okay, because you know that p minus 1 is equal to 2 power of st, right. So therefore using the similar technique you can obtain s LSBs x0, x1, x2 till xs minus 1, okay. But however obtaining the s plus 1th bit will be difficult, and if you are able to obtain the s plus 1th bit, like then exactly similarly what we have seen in context to p equal to congruent to 3 modulo 4, you can obtain the entire discrete log, okay. So therefore I mean the discrete log problem here will be difficult for this kind of beta when I is going from 0 to s, I mean t s minus 1, okay. But so therefore here in this part it will be easy, this will be easy, but Li beta will be hard when I is greater than equal to s, it will be difficult. Okay. So, it is difficult, again the hardness is difficult in the sense that if you are able to solve this problem, then you are able to solve the discrete log problem. Okay. So, when I say hard, it is an assumption, it is an assumed hardness, right. Is this part clear? Okay. So, now we shall conclude by some comments on the semantic security of ElGamal cryptosystems. Okay. So, in this case my objective is that I have been provided with the ciphertext for two different plain texts and I have to distinguish, right. I have to say from the ciphertext that whether x1 has been encrypted or whether x2 has been encrypted. Okay. So, for that let us just little bit recap the ElGamal cryptosystem. We know that E x comma r is equal to y1 comma y2, where y1 is equal to alpha power of r and y2 is equal to x multiplied with beta power of r for some random r. Okay. So, now you can use the Euler's criteria to test what? To test that, to test whether y1 and beta are quadratic residues. How? So, what you can do is this, right. You can actually, you know that I mean as an attacker you have an access to y1, right. So, therefore, what will you do is that you will raise y1 to the power of p minus 1 by 2 and check that whether it is equal to 1 or not, and from there you can conclude that whether y1 is a quadratic residue or not. Now, if y1 is, so you know that y1 is a quadratic residue is equivalent to saying that r is even number. So, you can derive the parity of r, right. Similarly, you know that beta is equal to alpha power of a and it is a public variable. So, you can again compute beta power of p minus 1 by 2 and from there you can conclude that whether beta is a quadratic residue or not. Now, if you know that beta is a quadratic residue, again from there you can obtain the information that whether a is even or not, right. So, therefore, using Euler's criteria from y1 and from beta you can obtain the parity of both r and a, right, and therefore, you can obtain the parity of AR, right. So, you can obtain the parity of AR means that you can actually obtain some mode information, like you can know that if AR is an even value, then you know that beta power of r is nothing but alpha power of AR. So, from there you can also conclude that whether beta power of r is a quadratic residue or not, right. So, therefore, one can actually use this Euler's criteria to understand that whether beta power of r is a quadratic residue or not. Do you see this? So, if beta power of r is a quadratic residue, then I can always write beta power of r as some value of alpha power of b, where b is even, right. Now, the other thing is that you know that if, so similarly you also know that y2 is some alpha power of you can say alpha power of c, okay, or that you know it is alpha power of r. So, you also know that from the fact that whether y2 is a quadratic residue or not, you know also that whether r is even or not, right. And what is x? X is nothing but y2 multiplied with the inverse of beta, right. So, what is y2? Now, y2 is alpha power of r multiplied with the inverse of alpha power of b, right. So, that is equal to alpha power of r minus b, yes or no, right. So, now you see that if x is a quadratic residue, then you know that r minus b has to be even, right. So, which means that either both r and b are odd or both r and b are even, right. So, which means that if I have got two classes of plain texts, say one class of plain texts where all of them are quadratic residues and the other class where both of them are non-quadratic residues. So, suppose I choose one value of x1 from here and I choose one value of x2 from this class of x2s, right. I do an encryption, ElGamal encryption on x1 and I do an ElGamal encryption of x2. Now, from this I can actually understand that whether x1 has been encrypted or whether x2 has been encrypted, because what I will check is the parity of these things, okay, and try to see that okay, whether both R and B are even or both R and B are odd. If both an R and B are even and both R and B are odd, okay, then it indicates, so if either both R and B are even and or both R and B are odd, then it indicates that X is a quadratic residue. You see that? Otherwise X is a non-quadratic residue. So summarizing, this is what it says here, that now this fact can be used to distinguish the encryptions of two messages x1 and x2, where x1 is a quadratic residue but x2 is not. Now it is an encryption of x1 if and only if both y2 and beta power of r are both quadratic residues or both non-quadratic residues. So one can stop this attack if beta is a quadratic residue and every plain text is required to be a quadratic residue. Okay, so you see that some extra conditions needs to be imposed to make ElGamal encryption also semantically secure, right. So I will give you one point to kind of some exercise to solve, like we have talked about beta is congruent to 3 modulo 4. Okay, so you can also take this problem of beta being congruent to 5 modulo 8, and suppose that A is a quadratic residue modulo P. Okay, so suppose one problem what you can do is that you can show that a power of p minus 1 by 4 is congruent to plus minus 1 modulo p, and if a power of p minus 1 by 4 is congruent to 1 modulo p, then you can prove similar to what we have done actually, that is prove that a power of p plus 3 by 8 modulo p is the square root of a mod p. Otherwise if it is minus 1, then you can show that 2 power of minus 1 into 4a raised to the power of p plus 3 by 8 modulo p is the square root of a mod p, and given a privative element alpha which belongs to zp star and given any beta which belongs to zp star, you can show that L2 beta can be actually computed efficiently. Okay. So this is an exercise which you can take and which you can try to solve. So my references have been from Stinson's book, that is for Stinson Cryptography Theory and Practice of Chapman Hall and CRC. You can get more details of what we have discussed, and in next test topic we will introduce the topic of elliptic curve cryptography.